Hi, my name is Vikram. Today we are discussing about RSA algorithm. First we look at the private key cryptography. Traditional private secret or a single key cryptography uses one key shared by both sender and receiver. If this key is disclosed, communication or compromised also is symmetric. Parties or equivalence does not protect sender from receiver forwarding a message and claiming is sent by sender. Probably most significant advance in the 300-year history of cryptography uses two keys, a public and a private key. Asymmetric since parties are not equal. Uses clever application of number theoretic components to functions. Complements rather than replace a private key cryptography. Public key, two key asymmetric cryptography involves the use of two keys that are the public key, which may be known by anybody and can be used to encrypt message and verify signatures, and the other is the private key, known only to the recipient, used to decrypt message and sign signature asymmetric because those who encrypt messages or verify signatures cannot decrypt message or create signatures. Let's see how it works. When a plain text is sent, encryption algorithm used, example RSA algorithm, where alias public key is used. It is transmitted through clipper text. Then decryption algorithm is done. Reverse of an encryption algorithm using the private keys of alias, and the plain text is obtained as shown in the figure. Why public key cryptography? Developed to address two key issues: key distribution. How to have secure communication in general without having to trust a KDC with your key. And second one is digital signature. How to verify a message comes intact from the claimer sender. It is where you can verify who is the sender. Public key characteristics. Public key algorithm rely on two keys with the characteristics, that is computationally infeasible to find description key knowing only algorithm, and encryption key computationally easy to encrypt or decrypt message when the relevant encrypt or decrypt key is known. Either of two related keys can be used for encryption with the other used for decryption. This is our public key crypto system, where message is sent, X is entered, and encryption algorithm uses key pair source KRA, and Y is given as output, and Y is again encrypted algorithm using an key pair source KUB, and the Z is sent, and Z is sent to the destination, where in destination the decryption algorithm is done using the key first KRB, which is key pair source, and y we will get Y, Then again we will decrypt using the KUA, where X we get X as output, which is an message. Public key applications. We can classify users into three categories: encryption or decryption. Digital signatures provides authentication, key exchange of session keys. Some algorithms are suitable for all users, others are specific to one. Let's see how it works. Communication channel. First, a message is sent using a secret key. Using that secret key, and the message, we get digital signature file, and with message and digital signature is sent to the Bob, where Bob uses the digital signature and uses private key to verify it is from Alice, where it is explained here. Alice computes a digital signature phi for the message M using her secret key SA, and the equation sigma is equal to SAM, which is here. Secret key and sigma is equal to SAM. Alice sends the message or signature pair M dash comma sigma to Bob. M dash comma sigma to Bob. When Bob receives M dash comma sigma, he can verify that it originally from Alice by using Alice public key to verify the equation M dash is equal to PA of phi, where it is used here. PA M dash is equal M dash is equal to PA of phi. If the equation holds, then Bob concludes that the message M dash was actually signed by Alice. If the equation fails to hold, Bob concludes either that the message M dash or the digital signature was corrupted by transmitting error, or that the pair M dash comma sigma is an attempted forgery which is been acted. Digital signature. Digital signature provides both authentication of an signer's identity and the authentication of the contents of the signed message. It is analogous to the handwritten signature at the end of written documents. A digital signature must be verifiable by anyone who has access to signature's public key. A signed message can be verified by one party and then passed to other party who can also verify the signature. A signed message is not necessarily encrypted. The message can be in the clear and not protected from disclosure. Security of public key schemas. Like private key schemas, brute force exhaustive search attack is always theoretically possible, but keys used are too large, that is greater than 512 bits. Security relies on large enough difference in difficulty between easy, encrypt or decrypt, and odd cryptanalysis problems. More generally, the odd problems is known. It's just made too hard to do in practice. Requires the use of very large numbers. We require very large numbers to use, hence is slow compared to private key schemas. Now we see RSA crypto system. In the RSA public key crypto system, a particular participant creates his or her public and secret key with the following procedure. First, select a random two large prime numbers p and q such that p into q, the prime p and q might be say 1024 bits each. Now compute n is equal to p into d. Select a small odd integer e that is relatively prime to n, which is p into d, which is by equation that p into d. Compute d as a multiplicative inverse of e. Then publish the pair pd, and which is a RSA public key. Then keep secret the pair sd, which is an RSA secret key. RSA user. To encrypt a message M, the sender obtains a public key of n recipient ku is equal to e comma n. Computes c is equal to m power e mod n, where m is lesser than 0 and lesser than n. To decrypt the clipper text, c, the owner, uses their private key kr is equal to d comma p comma q. Computes m is equal to c power d mod n. Note that the message m must be smaller than the modulus n. For example, we see the RSA example now. First we select p is equal to 17, q is equal to 11, and compute n is equal to p into q. 17 into 11 is equal to 187. Now compute phi of n, which is p minus 1 into q minus 1, which is 16 into 10 is 160. Select GCD of e comma 160 is equal to 1. Choose e is equal to 7, where we get GCD of e 7 comma 160 is equal to 1. Determine d is equal to 1 mod 160, and d is lesser than 160. Value is 23, since 23 into 7 is equal to 161 is equal to 10 into 16 is 10 into 16 plus 1. Public key publish public key ku is equal to 7 comma 187. Keep secret private key kr is equal to 23 comma 17 comma 11. Sample RSA encryption and decryption is: given message m is equal to 88, 88 is lesser than 187. Encryption c is equal to 88 power 7 mod 187 is equal to 11. Decryption m is equal to 11 power 23 mod 187 is equal to 88. RSA key generation. User of RSA must determine two prime of random p and q. The p and q should be large so that it will be difficult to find the prime numbers. Select either e or d and compute the other. Prime p and q must not be easily derived from modulus n is equal to p into q. Means must be significantly large. Typically guesses and use probabilistic test. Exponents e, d and or inverses. So use inverse algorithm to compute the others. RSA security. Three approaches to attacking RSA. Brute force key search. Infeasible gives size of numbers. Mathematical attacks based on difficulty of computing phi n by factoring modulus n. Timing attacks, a running of decryption. Thank you.